I'll be talking about how I use R and Neo4j together today, and just show you guys this tool set and the workflow I use day to day, and hopefully you can take something away from it that you find that you could use in your day-to-day workflow. So today that's going to include what is Neo4j? Who here knows what Neo4j is? All right. Who here knows what R is and have used it? Okay, great. Okay. Then I'll get into what is R Neo4j. And then the bulk of this is going to be a live demo in our studio. And then some next steps, some things you should do afterward if you like this talk, if you like the content. So what is Neo4j? And when someone asks me what Neo4j is, I like to start out with something that people are familiar with already, and then show how to take that and put that into a graph. So today I'll take you on a very short journey from SQL to a graph. I'm sure most of you are familiar with relational databases, how those work. And today I'll be showing how to model a data set from a SQL data set in a graph and the advantages of doing so. And when I talk about a graph, this is what I'm talking about. It is a collection of nodes that are connected by relationships. So first, let's look at if we had a flight data set and we wanted to model flights from around the world. We might start with the flights table, and we would have an origin airport ID and a destination airport ID to indicate, again, the origin and destination airport, right? And then there would be a foreign key pointing to the ID of the airport table with the name of the airport. And then let's say we also wanted to model delays. So we'd have a foreign key from the ID in the flight table to the flight ID in the delay table, because not all flights are delayed, so we have to put that in a separate table. We would also put how long it was delayed and the reason it was delayed. And then the reason would be an ID, and you'd point to another table indicating if it was weather or mechanical or whatever. And then let's say you also wanted to model diversions. So you would have another table, because again, not every flight is diverted. So you add another table with a foreign key pointing to this flight ID and a foreign key pointing from the airport ID to the airport table, and so on and so forth. So that's a pretty standard way that you'd model your flight data in a relational database. So with this, let's look at how we might model this in a graph. So in a graph, we have nodes and relationships. So we'd start out with the flight node type. We would have a bunch of flight nodes, and then we would also add all of our airport nodes. And then again, we want to model the origin airport for every flight. We would create an outgoing origin relationship from our flight nodes to whichever origin airport it was. And then similarly, for the destination, you would have a different relationship type called destination, outgoing from flight nodes to airport nodes to indicate that that's the destination airport, right? And then now we want to look at the delays. So we'd add another node called a reason node. It'd be weather or mechanical, again, whichever the reason is. And then if a flight was delayed, you would just create that relationship. There's no sense of null values. If a flight wasn't delayed, the relationship just wouldn't exist, right? And then finally, if you wanted to model diversions, you would just create that relationship if it were true, right? And so in our previous model, if I wanted to ask questions like, which flights from SFO to JFK were delayed for more than 10 minutes and also diverted, that would be several joins, maybe 7 or 8. And here you pretty much draw out the graph pattern you're asking for and retrieve your data by specifying a graph pattern, which with our Cypher query language, which you'll see in a bit. So this hopefully, maybe I should also say that all these nodes and relationships can have an arbitrary amount of properties attached to them. So for example, our flight nodes, you could have a flight number and a date property attached to it. The airport nodes would have a name property indicating which airport it was. The reason nodes would have a name. And then you can also put properties on relationships to just semantically describe what's going on. So this flight 123, was delayed for 43 minutes for weather. right? And then our graph query language Cypher allows you to query information from your database. So Neo4j, this pretty much sums up what Neo4j is. It's a graph database that allows you to store your information as a property graph like this and to query it with a graph query language. So now we have a vague idea of what Neo4j is. What is our Neo4j? So our Neo4j is just the R driver for Neo4j. It's an R package that allows you to connect to your Neo4j database and query information from it. It's a wrapper for the REST API. So for the most part, people will use the R driver for getting Cypher query results as a data frame in their R environment and doing whatever they want to do with it. And this is what my typical workflow looks like. So I'll have Neo4j at the top as my data storage, data persistence solution, our Neo4j in the middle to connect to the database, query it, and then within my R environment, plotting and modeling or whatever I see fit for this current data set. So,
Could I ask a question?
Yeah.
Can you go again to the difference between R and Neo4j and regular Neo4j?
Can you repeat the question too?
So the question is the difference between Neo4j and our Neo4j.
Yeah.
So Neo4j is a database, just like any other database, and our Neo4j is the R driver for connecting and querying that database from your R environment. Does that make sense?
Yep.
Okay. So the bulk of today, or tonight rather, is I'll be demoing the R package that I wrote and just showing how I use it day to day. And that's going to consist of prototyping data models, charting and plotting, and then finally graph algorithms. So this first part I'm going to demo is not something that I thought a lot of people would do, but I get a lot of support questions about it. So I'm going to go over it. These are, this is what I find myself doing it sometimes too. We're going to first load the R Neo4j library and then connect to my currently running Neo4j database, which is at this URL. And maybe I should, and that's going to start the connection to my database, and that's going to return a graph object that I pretty much pass as the first parameter to most of these functions for talking to the database. So first things first, I'm going to just delete everything in the database just because I'm playing around here, and I'm just going to do some quick prototyping. So this is nice if you're not familiar with modeling data in a graph, you're not interested in learning our query language quite yet, you just want to play around with the idea of modeling your data in a graph. So the first thing I do, always do, is add a uniqueness constraint. So I'm going to say here that this is going to be the node label. So remember we had airport nodes, we had flight nodes. I'm going to say person nodes need to be unique by the name property. So go ahead and do that. And now I'm going to use create node to create some nodes in my database. And these are all things that will also be stored in my R environment in memory. I'm going to clear that actually. So here we're going to use the create node function, which just, again, we're going to pass that graph object first, and we'll specify the node label here, and then you can, as I said, you can add an arbitrary amount of key value pairs to all the nodes in the database, and I can do that here, concatenated at the end of this function. So I'm going to go ahead and create all these nodes, and that's going to create those node objects in my R memory. Yep.
What is the name of the repo?
Oh, I'll do that at the end. So these are all, I call them node objects in R, and we can see all the properties on them with the standard R functions names, and then I can access those with the $sign operator, which I'm sure if you've used R, most of you are used to that functionality. So that's created a few nodes in my database, and I added that uniqueness constraint because if I, for example, tried to create another Nicole node, I would rightfully get an error. So of course you don't want to duplicate your data, so it's good to be using the database type things available to you. So now I'm going to add some more nodes. I'm going to add some board game nodes and computer game nodes. So I'll go ahead and add those uniqueness constraints now. And I'm going to create some more nodes here. So again, I'll use create node, passing that graph object, saying that it's a board game. I'm going to add name and max players properties on here. So I'm going to create Risk and Settlers, these two board games, and I'm going to create two computer games, League of Legends and StarCraft. And again, we can access those with the $sign operator. And here I'm showing off all the different properties that you can put in a Neo4j database. You can put strings, you can put Boolean true false, and you can put numeric, and you can also put collections or arrays or vectors, or however you want to think about that. So right now we just have a bunch of nodes in our database, and we want to start creating relationships. We can use the create rel function to do that. And the syntax there is it first takes the from node as the first argument, the relationship type as the second argument, and then the to node as the third type. And then after that, it's an arbitrary amount of properties that you can attach to that relationship. So here we're going to say that Greta plays Risk, and she plays color red. So that's going to create a relationship object in my R environment. And similarly, you can access the properties with the $sign, and then there's a lot of functions. I can, for example, get the start node of that relationship. I can get the end node. And then all the functionality available to you is listed over here. Most of you probably know this in the index. So when you do load it, you can see all the functions available and all the documentation. So there's a lot of stuff that you can do with relationship and node objects within R. So that just created one relationship. Now perhaps we want to create some more relationships. So I'm going to use the apply family of functions, because everything in R is a list or vector or something of that sort. So I'm going to apply over this list of node objects, both Risk and League of Legends. And for each of those, I'm going to create a relationship from the Hank node to those games. So again, we're just iterating over these nodes and applying this function over them. And that's going to, for both of these, return a list of relationship objects. And you can use you can use list as you see fit to iterate over and do whichever operation you want. So for those, I manually passed in these. I typed in the list here, but more likely you'll want to, in a more automated way, fetch those nodes from the database. So here I'm going to use the getNodes function, which allows me to retrieve a list of node objects from the database using a Cypher query. So this is our first hint of Cypher in here. It's pretty SQL-like, aside from the match clause, which I'll show a better example later. But this is matching on any node where the node either is a board game or the node is either a computer game type node. And so that's going to return to me a list of node objects. There should be 4. And I'm going to apply over those again, and I'm going to create a relationship from myself to all of those. And so now I've created this data model, and I played around with it from the comfort of my R environment. And then I finally wrote this, this browse function that will pull up the browser and the relevant URL. And this is actually, we're talking to the database now. I mean, we always have been, but this is our browser tool where you can visualize your data. So this is everything we've just created. And we can see all the properties that we've added are on here. And we can visualize what we've got in here. So it's just, it's a workflow that I didn't think people would use much, but I think people like the idea of being able to manage all of their R objects in a graph and persist it in a database, because they don't want to, for example, save an edge list to some CSV file or save some iGraph object to an R data file, because that's not very robust. Yeah?
So is every object in your R environment also within the graph now? So there can be no objects in your R environment that are not in the Neo4j database?
So the question is, are all my R objects in the database right now? Yeah.
Are there any R objects that are not within the database?
I mean, if it's an R object not related to Neo4j, for sure. Like if I do, I'm not sure if I understand your question. X equals 3, I mean, that's not, you know, in the database.
Okay.
Is that, but then, so you have to be careful though, because if you do something like update property on Nicole and say, and I don't reassign this. So if I do that, it's updated the Nicole object in my R memory, but it hasn't done any, and it's done it in the database, but, sorry, I said that backward. It's updated in the database, but my Nicole property is, or my Nicole node is now out of date because I didn't reassign it. I would have to say Nicole equals, and then my in-memory R object would be up to date. I said that backward. The database is updated when you do functions like that. You just have to be sure to reassign it, right? But yeah, it's not. There's nothing that's connecting it real time. Once it becomes in your R environment, it's static. There's nothing keeping it up to date unless you're doing stuff like that and you're manually, yeah.
You put a data frame as one of the key value pairs?
No. So it's got to be. It can be a vector, and you could get fancy with that, but and it all has to be the same type. You can't do some. I'm pretty sure this should give me an error. You can't do something like. You can't do different. Usually, so I'm not sure what it did there. Usually in Neo4j, you cannot put different types within a single collection as a property. It's got to all be numeric or all be Boolean. I'm not sure what it just did there, actually. So that's just a quick way to prototype data models within your R environment and hold everything in memory and just play around with different stuff, because now I can just, you know, clear the entire database and start over and just quickly.
I think it coerced true to a string.
It coerced true to a string?
Yeah, if you look at the response, it's two strings.
I'll have to look at that. You should make an issue request on my repo. Okay, so moving along, for the most part, at least for me, and I think for most people who use my package right now, they, you know, something else is updating and maintaining the database, and they're tasked with connecting to this database and exploring it. So I'm going to connect to a database here that I already have up and running. I wrote a script that, excuse me, is collecting, or not right now, but collects tweets with hashtag rstats and adds them to a Neo4j graph database. And so I'm going to connect to that right now, and we're going to start exploring it within R, and just to figure out what's available in this database and what I can do with it. So I wrote this summary function that will do what we refer to as the what is related and how query. So these first and third columns right here are node types, and then that middle column is a relationship type, and it's finding every combination available in Neo4j between your nodes and the relationships between them. So we see here that, I mean, like I said, this is a Twitter data set, but we see that we have users posting tweets, we have tweets retweeting other tweets, tweets can mention users, hashtags can tag tweets, so on and so forth. So the summary function is good if you've connected to a database and you're just wanting some quick overview of what's available. And we can also do get constraint. That'll show us all the uniqueness constraints that are currently active on our database, and these are also indexed. And if it's possible that you would have indexes that are not uniqueness constraints, but either way, we can get that information, and so we know what indexes are active and available to us. And I'm also going to I'm interested in these user and tweet nodes. I'm interested in what properties are available on these, because I'm not sure, perhaps. So I'm going to use the get single node function, and that's going to I pass in that graph object again, and then I use a Cypher query to just get one of something. And here I'm just going to get a random user and return them. And now I have this user again as a node object, and I can see all of the properties available by calling names, or I could just print it to see what these properties are. We see that we have their image URL, how many followers they have, how many people they're following, location name, so on and so forth. And similarly, I want to get a random tweet and look at that. So now I know that I have user nodes with the aforementioned properties, and I have tweet nodes that have properties like favorites, how many favorites it's gotten, its date, its text, and its ID. So in a few lines, we've connected to the database, gotten some random stuff from it, and figured out what our model looks like and some of the properties that we can ask for when we start writing queries. So this next part, I'm going to start using the Cypher function that most people use for everything in this R package. It's going to allow you to retrieve Cypher query results as a data frame. And then, of course, once you have it in a data frame, you can do all the stuff under the sun that R has to offer that you can do with data frames, right? So here we're going to get more into the Cypher query language and how you query stuff from Neo4j. Again, the match clauses should look unfamiliar if you haven't used Neo4j, but then it's pretty SQL-like with count and distinct and order by and limit. So these match clauses, you pretty much draw out what you're asking for from the database. Here we're matching on tweet nodes, and then we're optionally matching on hashtags tagging those tweets, and then we're optionally matching on tweets retweeting that tweet. And then we're going to return the tweet's ID. And you access properties by identifier dot key. And then the count of hashtags, the count of retweets. And here we're just going to get a pretty straightforward data frame that's going to tell me, that's going to have these two columns that I've asked, or these three columns rather, that I've asked for, where we have just these two columns of hashtags and retweets. And this is just to show that even with a graph database, which might seem unfamiliar to you, you can still do all the classic stuff you're used to doing, like let's find the correlation between number of hashtags and number of retweets, right? So now that I have that in a data frame, and I got that pretty easily, I can use the correlation function to do that. And then another pretty basic thing, I want to create a linear regression, just a simple linear regression where retweets are a function of how many followers someone has. And this is the query that's going to get that information for me. And again, you just use the Cypher function to get that information out. I'm going to match. So here I'm matching on this graph pattern. I'm matching on user nodes with outgoing post relationships to tweet nodes. And then optionally matching on other tweets retweeting that tweet. And then for each user, I'm going to count how many retweets they've gotten total, and then return the properties that I want, right? So again, a pretty straightforward query to get this information out. So now I have followers and retweets, and I can use the linear model function in R, which is pretty basic, to create a simple linear regression. And so just in a few lines, I was able to extract that information out. So again, these are just an example that all the standard stuff you're used to doing is still possible in a Neo4j graph database. So now I'll go on to some plotting. A lot of people will use R solely for plotting because it's hard in Python, and it has a lot of good plotting libraries like ggplot. Today I'm using Google Viz because I don't use it very often, and I think it's pretty. So here I'll just be making a pretty straightforward bar chart. Again, I'll be matching. I want to get the top 10 most mentioned users and plot that for whatever visualization purposes I have. So again, I'll be matching on tweets mentioning users. I'm going to return their screen name and then the count of how many times they've been mentioned, and order and limit to get the top 10. So that should give me a data frame that looks like that. And I'll use Google Viz's gviz column chart to very quickly plot and look at that. Was it worth it? Yeah, it was. Okay. So yeah, I mean, just to show that you can quickly pull information out and make some quick visualizations. This next one is fun. I like looking at hashtag co-occurrences in Sankey diagrams. So this query is a bit more involved, first I'm getting the top 10 hashtags just by a count of how many times they've tagged a tweet, and so first I'm matching hashtags, tagging tweets, and then I'm omitting our stats because it's on everything, and I'm ordering and limiting just to get the top 10. And then with those top 10, I'm doing my standard match hashtags. So here I'm getting hashtags that mutually tag a tweet, right? That next line is just a fancy way to avoid cycles. And then I'm returning the 2 hashtags and then the count of how many times that they have been mentioned together. So that should give me a data frame that looks like this. Again, hashtag 1, hashtag 2, a count of how many times that's happened. And now I can easily pass that to the gviz Sankey function to visualize that. And so I think that's a really fun way to showcase, Neo4j is really good at storing data like that, and it's also really good at letting you extract that information out for making quick analyses like these. So you can see that things like, Python isn't, directly mentioned with analytics, but it's mentioned with statistics, and statistics is mentioned with analytics, and so it's just a fun way. Yeah?
On 63 in your Cypher query, what does that just use the object ID to compare?
Yeah, so because they're going to be so every hashtag is going to be matched once on the left and then once on the right, and this is using their internal IDs in the database so that they're only found on one side, right? It's just so that it's not, because otherwise I would have statistics deals, or I'd have data science R2, and then I'd have R data science 2,
Right.
and it's just redundant, and yeah, it's just a way to avoid that. And finally, for the visualization, I want to make a word cloud. Anyone use the text mining package in R, the word cloud package in R? All right, you're in for a treat, because so I'm going to load the word cloud package and all this other stuff that's going to help me clean up the text. And here I'm going to use the get nodes function. This is an R Neo4j function where I'll pass the graph object and use this Cypher query to get tweets that only have the text property. So that will return to me a list of node objects. And we have 623 nodes. And then I'm going to supply over that list of node objects, because remember our tweets have this text property. So I'm going to supply over that to extract that out into, so now we just have the tweet text. It's a character vector. And then I'll use some of the stringer functions to get rid of links, or to convert everything to lowercase. And so this is just more, most of this is shamelessly copied from the documentation, so I'm not really doing anything super fancy here. But this is going to create a text corpus and remove punctuation, all that good stuff. And then finally, we're going to create a term document matrix out of our corpus here, and do some more data manipulation. We're convert it to a matrix. We're going to sort it. And then finally, get to this, where we've taken all the text on our tweet nodes from our database, run it through a few lines, and we have a term frequency data frame. Pretty straightforward. And I'm going to get some colors for our word cloud. And I need to make some room for it, because it doesn't like it when it doesn't have room. And finally, I'll pass that information to the word cloud function. And you can see a pretty fun visualization of the tweet text from the tweets that I've collected with hashtag #rstats. OK, so that's just a quick demonstration of the types of visualizations you can do. Obviously, you can do whatever R has to offer that you can do with a data frame, which is a lot of things. And now I'm going to move on to the most fun part, I think, and I have to jump into a little spiel here, is to compare and contrast real quick a graph database from a mathematical graph and how you use them differently. So this is the data model that we've been looking at for the past few minutes. It's pretty intricate. We have different types of nodes. We have different types of relationships. There's text properties, numeric properties. And it's really good at storing and letting you query information from it. But when I'm wanting to do something that's more graph analytics, this is the type of graph I want to do that on, right? So this is a mathematical graph, and there's not really a notion of node types and relationship types. There's not text properties, obviously. It's just a collection of nodes that are possibly connected by edges and possibly weighted and possibly directed, right? And if I want to ask a question like, what is the betweenness centrality of every single node in my graph? This is the data object that I want to do that on. So let me explain my workflow when I try to do stuff like this. So I'll have Neo4j at the top, storing my graph database, storing this intricate data set of tweets and users and hashtags, and then I can think of a million ways that I can coerce or infer that type of graph out of my data storage solution. So I'll use Neo4j in the middle to ask these types of questions. So for example, when I look at this, I see, oh, perhaps every node can be a user, and 2 users are connected if they've both tweeted the same hashtag, and it's weighted by how many times they've done that. Or maybe each node is a link, and they're connected if they've been tweeted together, or something like that. So again, when I want to do these graph global questions, like finding like an expensive question like betweenness centrality, which is you find every single shortest path in the graph and then count how many times a node is on that path. It's an expensive question and something that I like to do on a mathematical graph. So let me jump back into R. So again, I'm connected to the same database, and now I want to ask what, I'll refer back to that same example I used. I want to extract out of it 2 users, or any 2 users that have posted a tweet that are tagged by the same hashtag, right? And that's going to give me all the users who have posted the same hashtag. Again, I'm omitting our stats, and I'm going to return their screen names and the weight of how many times that happened. So just in 3 lines, we're able to extract that information out. And this is what, does anyone here use iGraph? Okay, great. So iGraph is a network analysis tool in R. It's an R package that will do all the fancy graph analytics that you're probably aware of, like betweenness centrality, graph clustering, all of that fun stuff. So this is what it refers to as an edge list. So I've used R Neo4j to extract this edge list out. And now I'm going to create an iGraph graph object from this edge list that I've coerced out of my database. And so I'll use the graph data frame function. This is an iGraph function to do that. So now I have this iGraph function, or this iGraph object rather, and we can visualize what so this is a subset that we've grabbed out of our database. This is, again, users connected if they've tweeted the same hashtag, weighted by how many times that's happened. So we can visualize, and I think iGraph is a pretty good visualization tool for just some quick stuff like this. And now I'm going to ask my, find me the betweenness centrality of every node in my graph and show me the top 5. So here we see that, and this was kind of a fun exercise because I had never heard of DataRobot, but it had a high betweenness centrality, and so I went and checked it out, and now I have follow someone new on Twitter. So it was a fun exercise, and when someone has a high betweenness centrality, you can think of them like this node right here. I don't know if you can see where I'm pointing. Probably has a high betweenness centrality because it's connecting 2 communities in the graph, and that's what betweenness centrality is doing, or that's what it's calculating. And then I can do stuff like making every node, the size of a node, a function of its betweenness and plot it. So it's just an easy way to manipulate your graph and visualize it that way. And iGraph, again, like I said, has all these graph clustering algorithms built in. So I'm going to go ahead and run the edge betweenness community algorithm. That's the Gerben-Newman community detection algorithm that you can read about on your own time. But we can easily run that on this subset that we've grabbed out of our database, and I'll get some colors and then just replot it with that. So just a really easy way to very quickly grab a subgraph, if you will, out of your database and analyze it all within R and visualize. And so, and just to show how easy it is to switch gears, let's say I change my mind and I don't want to look at this particular subgraph anymore. I now want to look at a subgraph where each node is a hashtag and they are connected if they've tagged the same tweet, and their edge is weighted by how many times that happened. So again, that's just a 3-line query so I'm going to overwrite the query to do that, and I can easily get that out. So now I can just run the same script now and do a similar analysis on what is now a different subgraph, and it's smaller because there's less hashtags than users. But so that's what that subgraph looks like, and we can do the same thing with the betweenness. We see that R and data and statistics are high on betweenness centrality, not too surprising. And right, we can just do the same things here. Visualize as a function of betweenness. We can run the same clustering algorithm. This is also good if you're trying to compare graphs that are defined differently. Perhaps instead of defining a user's edge weight by how many hashtags they've tweeted, it could rather be how many times they've mentioned each other. So it's a good way if you're looking to compare analyses by how you redefine what your subgraph looks like. Right, so I think these are the most common ways that I see the package being used. It's people who just want these low-level API functions for just the comfort of managing your data in a graph, and then for the most part, people using the Cypher function to coerce data frames out of their database for plotting or just really basic exploratory analysis. And then I've seen a few people do this with really cool analyses on top of what I've shown here. So those are the 3 main ways I see it being used. This was I kept it high level because I just want hopefully to show there's at least one thing that touches you, or you see that could be helpful for you. But my colleague Mark Needham does a lot of really cool blogging on how he uses. I'm going to post all these on the meetup too, by the way. But you can take pictures anyway. He has a really cool data set actually of meetup groups in London that he stores in Neo4j, and then he'll query it and do lots of cool stuff within R using the R package to connect to the database. And he does a lot of cool stuff like what's the best time to announce a meetup group or announce a meetup event and stuff like that, which R is very good at letting you do time series type stuff like that. And then that's my blog, and I pretty much constantly blog about R and Neo4j. So you'll see a lot of good content there if you're wanting more on top of what you've seen today. And then for you, here's the GitHub repo. And then also, all the code I showed today is on my GitHub as well if you click around. But this is the R Neo4j repo. You install R Neo4j with DevTools, because I haven't put it on Cran because I change it too often. But it's really easy to install with DevTools. It's 3 lines, right? And then I have all the documentation. If you, for some reason, want to read the documentation before installing, all the functions are documented with examples on my website. And then all the code from today is right here. And so you can go look at that. It should be all the same. And I also have instructions on how to create your own Neo4j database of tweets. The same database I showcased today. You just run a Python script and away you go. So right, and then yeah, if you look around my GitHub, you'll see a lot of examples of R and Neo4j together, just for different ideas you might have. That is all I have for you today. MIT. Oh, of Neo4j?
No, yours is MIT?
Yeah, it's all MIT, right? Yeah. Any other?
Yeah,
Oh, so who wants to tell the story? Anyone? Well, so apparently back in the day, I think our code was hosted on SourceForge, and it was a thing back then if your code was written in Java to put 4j at the end of something, and then our founder was into the matrix at the time, and so just tacked 4j on the end of Neo, and that's actually the example data set that ships with Neo4j. If you go download it, it's a movie data set, and all the matrix characters are in there and all that good stuff. So, right.
So I do think we have some time for some more questions. I just want to quickly say a few things. First of all, I'm Greta. I'm with Neo4j. We do have our own meetup group, Graph Databases San Francisco. Look us up on meetup.com. Next week, if you want to learn more about Neo4j, we're hosting Intro to Neo4j, so it's all the fundamentals. It's just going to be down the road on Montgomery at ThoughtWorks. It's next Tuesday, I believe. If you just go to neo4j.com/events, all of our meetups are there. We have a bunch of webinars scheduled coming up. And then the main thing is that we have, at the end of October, our big user group for graph databases and applications. It's going to be hosted here in San Francisco at SF Jazz. I'll connect with Molly to send you guys all of discount codes so you can register with $200 off. It's going to be really great. We have a bunch of speakers from eBay, Pitney Bowes, UBS, Crunchbase, all coming to talk about how they use graph databases and applications. So definitely check out neo4j.com. We're open source, so also play around with Neo4j itself.
Yeah, you can go download it right now and play with it on your local machine. Also, yeah, I'll post all links on the meetup page. So you don't have to worry about memorizing all that. Yeah?
How does this whole thing work with large volumes of data? Like, if you have a few million tweets in your graph database, would this work?
Well, so the question is, how does this work if you have millions of nodes, right? Well, you know R. I mean, it holds everything in memory. So you'd have to be running R on a pretty powerful machine if you wanted to pull actually 2 million node objects into your R memory, right? So I mean, that's just that's true everywhere, where it's a function of how much do you want to pay for it to scale.
Does it work with packages like SF, which tend not to load all of the data into memory and work off of the disk? Is there any such interface right now?
So the question is, does it work with packages that let you use the disk rather than RAM? And I don't know. I haven't looked into that ever. I've always just held stuff in memory with my standard R default environment. But I'm sure you could figure it out. Let me know. Yeah.
What is the spelling of that algorithm you said that was found the most times on the shortest path?
So that's the, you'd have to go read about it.
That one and the other one.
There wasn't, this is the one so the question was, what's the name of the algorithm by which I found the community detection algorithm? It's the Gervin-Newman. It's pretty straightforward, actually. The paper is actually better to read than the PDF that the guys actually wrote is better than the Wikipedia article, I believe. But yeah, that's just a community detection algorithm.
Okay, you did it. It was really simple. Like how you did it. How did you do it so simple?
Well, iGraph did it. I didn't do anything. iGraph did it. So, so I wrote the query that got that subgraph out of my database, and then I had that stored in my. So this G is just an iGraph graph object, and then edge between this community is iGraph code that runs that algorithm for you and returns the cluster membership as a vector. And again, all this code will be online, so you can definitely look closer at it, and you can read all the details on how this function works. But yeah, it's super easy. Once you get something, some subgraph into an iGraph object, you can do. And if you go to iGraph's website, you can see all the stuff that they have. It's quite a lot. I haven't run anything that iGraph couldn't do in terms of graph algorithms. All right, thank you. Well.